All right, so today we are going to continue addressing homogeneous equations and characteristic equations. But this time I'm going to focus a little bit on what we call repeated roots. So just a quick example from the past. So consider this general ODE. It's homogeneous. It is second order, and the coefficients happen to be constants, which is nice. The corresponding characteristic equation, if you recall, is r squared minus 2r plus 2 equals 0. I used the quadratic formula, and I got 1 plus or minus I. Now, in the past, we said, okay, one of the solutions is going to be e to the 1 plus I t, and then the other one is going to be e to the 1 minus I t, and we can use Euler's equation to make this look a little nicer. And you can do that if you want. I chose to basically just pick one of them called 1 plus I and run with it, because you'll get the 1 minus I for free anyway. So r equals 1 plus I is one of the solutions. We used to call it y1, right? y1 and y2. So my corresponding solution to this will have to be e to the rt, right? And if you recall, we just split this, e to the t times e to the it, which is e to the t times this cosine t plus I sine t, which can also be written as, if you care, as e to the t cis t, okay? So, just from this equation, just from these roots, I know my two solutions. It's e to the t cosine t and e to the t sine t. And therefore, the general solution will have to be a multiple of this plus a multiple of that. Remember, you can never turn cosine into a sine. So these are separate solutions. So from these two together, you can generate or get the general solution. Now, I could use, again, 1 minus I and go through the process. And basically, you're going to get e to the t times cosine t minus I sine t. And you'll get this type of solution. So it doesn't matter. I like to just pick one of them and then break it into the two pieces. These are my two. This is my set of solutions, and this is my general solution. Now we're going to consider a different homogeneous ODE, second order, constant coefficients, just to make life easy. So the coefficients are 1, negative 2, and 1. And the corresponding characteristic equation is this. And this turns out to be a perfect square. And that is a huge problem. Because clearly, if this is the roots, then e to the t is the roots. And you can't say, well, then the other root has to be also r equals 1, and therefore I have another e to the t. Well, e to the t is a multiple of e to the t. You're not generating all the solutions anymore. So we've got to figure out a way to figure out the second one. So what I'm going to do is I'm going to play a little trick. So we know y1, we know y1 is e to the t. E to the rt, and r is 1, okay? So how do we get the second one? So what I'm going to do, I'm going to assume the second one is r equals 1 plus some little epsilon for some positive epsilon, which means my factors are r minus the 1 and r minus the other root, which is 1 plus epsilon. Which means my actual solutions are e to the t, and in here I have e to the my roots t, right? That gives me this general equation, ODE. Now, you might say, well, where is this coming from in this, okay? So all I did was I foiled this, basically, literally foiled this. And then from there, I pulled, so if I know this, I know this, right? So if I know this, I would know this. Actually, let me just do it quickly. It's no big deal. So I'm gonna foil this very quickly. Okay, put it in green. I'm gonna get r squared minus r. Actually, let me slow down here. You're not gonna know what I'm doing here. So first I'm gonna clean this up, foil this. Okay, so we have r minus 1 times r minus 1 minus epsilon, which is r squared minus r epsilon. Finished with this. Now I'm going to go to negative 1. Negative r plus 1 plus epsilon. So which is r squared. You have a negative r epsilon. So I'm going to call it negative 2r minus r epsilon for now, plus 1 plus epsilon, and which is r squared minus 2 plus epsilon r plus 1 plus epsilon. Okay, so that is the characteristic equation. Let's go back here. If my characteristic equation is here, then I can easily go back and figure out the ODE from which it came, right? So if I look at this, I know I have y double prime by itself. Here it is. I have negative 2 plus epsilon y prime. Here it is. And I have 1 plus epsilon y. Here it is. If you have a 1, you get a y. If you have 1 plus epsilon, you get 1 plus epsilon y. So this is the ODE whose roots are these. Of course, I haven't mentioned that we just added epsilon, but we're going to force epsilon to go to 0 because the roots are r equals 1 repeated, right? So this is really truly not a root. This is a root only if epsilon goes to 0. And that's what we're going to do next, okay? So here is my general solution. So this equation has a general solution, and that general solution is a constant multiple of this plus a constant multiple of that, right? So the general solution is y equals constant multiple of the first one plus a constant multiple of the second one. And here is my first, and here is my second, okay? So I just wrote this. You know what? This is exactly this, okay? I'm going to just impose a couple of initial conditions to get a particular solution to this general solution. This is general, and I want a particular solution. So if I plug in 0, y of 0 is 0. So if I plug in 0 here, I get e to the 0, which is 1. So c1 plus c2, because that's 0, e to the 0 is 1. So c1 plus c2 is 0 given. And then I'm going to do the same thing for y prime. Let me do y prime quickly for you. So y prime equals c1 e to the t plus c2 1 plus epsilon e to the 1 plus epsilon to the power of t. And now I'm going to plug in 0 for t and force the response to be 1. So e to the 0 is 1. So you get c1, here it is. And e to the 0 is 1, so that kills this whole piece. And that leaves me with c2, 1 plus epsilon. Here it is. And the output is 1. Okay? So I just did some simple, kind of the magic of algebra 1. I got c1 and c2. So these are my two constants, and therefore this is my particular solution. Particular. Okay, so this is my particular solution, and that's my general solution, this one, or this one actually, general. which is a linear combination of the two solutions we guessed. Okay? So now, so my particular solution is this. You know what I'm heading at. I'm going to have to take a limit as epsilon goes to 0, right? Because I really want to get a solution void of epsilon. Epsilon should go to 0. We know this is one solution. We need to try to guess another one by forcing epsilon to go to 0. So I'm going to clean this up first. This one is e to the t times e to the epsilon t. So there's an e to the t here, and there is an e to the t here. I fractured that out. So that leaves me with negative 1 over epsilon plus the leftover from here, which is 1 over epsilon e to the epsilon t. 1 over epsilon e to the epsilon t, okay? Just clean this up, put it in the same denominator, and I got that. So now I'm going to take a limit as epsilon goes to 0 of this quantity. Now remember here, at this particular moment, epsilon is going to 0. So this is a constant as far as this is concerned. This is a constant. You can pull that out, okay? So let's not look at this. We're just going to multiply it later, okay? Imagine I put, basically what I'm doing here is this. E to the t limit as epsilon goes to 0 of this, okay? So don't let this bother you. So that's going to stay, okay? Now, if you plug in epsilon here, 0 for epsilon, you get e to the 0, which is 1. 1 minus 1 is 0. And 0 over 0 is undetermined form. I basically use L'Hopital's rule because I'm allowed to. This is in the form 0 over 0, so you could use L'Hopital's rule. And L'Hopital's rule says if what you do is you get limits of this, the derivative of this divided by the derivative of that. Remember, your variable is epsilon, okay? So I get, that's going to give me 1. Let me write it down in green, maybe. Limit as epsilon goes to 0 of negative 1 plus e to the epsilon over epsilon. The derivative of epsilon is 1. And the derivative of e to the epsilon is e to the epsilon. And negative 1 disappears because the derivative of negative 1 is 0. And so I'm not done because I have a limit as epsilon goes to 0 of this. And this is, I made a mistake. There is a t here. And that's going to give me t e to the epsilon, right? Remember, your variable is epsilon. Sorry, I don't like when things are not clean, so let me just slow down. Okay. Equals limit as epsilon goes to 0. The derivative of the bottom is 1. And the derivative of the top, derivative of negative 1 is 0, and derivative of epsilon t is t e to epsilon t. Okay? Now, when epsilon goes to 0, e to the 0 is 1, and you get just t. So I'm going to go back here. So limit of this quantity is t, and e to the power of t sticks around, and this is a beautiful answer. From your reading, you were trying to get particular solutions to the homogeneous, and you talked about in the discussion board, well, how do we guess? We can't just keep guessing and checking. Generally, the way it works is one of the solutions is e to the t, and the other one is t times e to the t, okay? So these are your two, your sets of solutions, which can give you the general solution called C1 e to the t plus C2 t times e to the t. So that is really shocking. That's the other solution is just a product of the old one with t. Okay, and notice that you cannot generate this. Is not a multiple. This is not a multiple of this, okay? So we couldn't just say, okay, well, let's just stick in at 3 or something. So that's a function of t, actually. Okay? So I'm going to do a quick proof, and I will end this presentation. So imagine we have a characteristic equation of a homogeneous ODE. Again, I'm just using constant coefficients. And imagine R is a repeated solution, as we just did. Now, in here, R was 1. So I'm just using e to the t, right? R is 1. Let's go back here. R is 1. I'm doing it in general here. Imagine your solutions are e to the RT, and we're going to guess the other one by multiplying this one by t. I'm going to double check to see if it is a solution to the corresponding ODE. Well, the first one is very quick, this one. So if this is a solution, the derivative of this will be r e to the RT. Second derivative will give you r squared e to the RT. Then I'm going to plug it in here. So y double prime minus 2r y prime plus r squared y. Pull out r squared e to the RT if you care, because we know it's not 0. So that leaves you with r squared minus 2r squared plus r squared, which is 0. So we know, we knew this before we even started, that this is a solution. Should this be a solution? You know, this tells me maybe yes. Well, let's see if it works. So here's my second, my solution of the other pair, of the pair. It's always a pair. So we have t to the RT. The first derivative will give you, this is a product rule. Remember, your function here is a function of t. So product rule gives me derivative of t, which is 1 times ERT, plus t, derivative of this, drop the r, and you get this. And I don't want to leave it like this. I want to factor, because it's going to make my life much, much easier. So e to the RT is factored, you'll end up with 1 plus RT. That is y 2 prime, because I need y prime and y double prime. So here is y prime. Second derivative, I'm going to differentiate this. I'm going to use the product rule. The derivative of this is RERT times the second piece plus the first piece times the derivative of the second. I'm just using product rule, okay? FG prime equals F prime G plus FG prime. That's all, okay? All right, and I am going to, again, factor out e to the RT. That leaves me with r plus r squared t plus r. So twice r plus r squared t, and you have this. So now we have y double prime, we have y prime, and we have y. We'll plug them in. So y double prime is this, literally just copy, okay? Minus twice r y prime. Here is y prime, because we found this earlier, plus r squared y. Y is your solution, right? I foiled and I pulled out ERT once again. So that left me with 2r plus r squared t, 2r plus r squared t, minus 2r, minus 2r squared t, plus tr squared. Okay? Those two cancel with this. These three cancel, and these two cancel. And once again, you get 0. So hopefully this is going to take away from this guessing and checking on trying to guess a second solution if you have a perfect square. Basically, we had a perfect square. Okay? So what I would like you to do for homework is really short. This is an assignment you've done before, and it was a little hard for you at the time. But now that you know how to solve homogeneous equations, this is the spring system with no damping. It's just MA equals negative kx. This is the spring acting on the mass force, right? You could look at it this way. MA equals negative kx. I'm using vectors. Okay. So very simple. Second order, homogeneous. Constant coefficients, which is nice. Say thank you. Constant coefficients. They don't have to be. Remember, this is a function of t. This could also be a function of t. There is no forcing term. It's not homogeneous. It's not non-homogeneous. It is homogeneous. I would like you to solve it. Sometimes we write it like this, right? Some people they don't like this. They divide by m, everything. M is not 0. So it's easy to solve now that you know a little more. And then I would like you to work on the spring system ODE that also involves damping. This is the damping force. It's actually negative this, right? So basically you have what am I saying? M d squared x dt squared equals negative kx, that is the force acting on the spring, minus p dx dt, right? This is the dx dt. So this is called the damping force. The p is called a damping constant, right? P is the damping constant, and this is the damping force. They are both negative, obviously, because they are acting on they go contrary to how the spring is moving, so they pull back. Maybe later we can even do this. You can do this now, but you'll be interested to work this out. I'll put it in green. Don't do this now yet. Okay, so you have m d squared dx dt squared plus the resistance force, right? Plus the acting force on the system. Instead of having 0, we will have another applied force. I don't know, g of x, g of t. Or, you remember we called it r of t, or r of x. If you remember, this is the forced function. Okay, so that would be non-homogeneous. So these are homogeneous, but we can add an acting force on the system, and we will be able to solve that once we address homogeneous equations in the next video. All right, thank you so much for listening, and have a wonderful weekend.